Welcome to Herdley, where each book is distilled into a chronological story, offering you a special journey in just minutes. Today, we study together Kate Kitagawa's book, The Secret Lives of Numbers, a hidden history of math's unsung trailblazers, in which we probe into how mathematical discoveries have often been misattributed, overlooked, or erased, shaping a distorted view of history and the individuals who contributed to the evolution of mathematics. Kate Kitagawa is one of the world's leading experts on the history of mathematics. Timothy Revell is a science journalist and lapsed mathematician who is currently executive editor at New Scientist. Don't go away. Herdley the editor will be right back with the story. Picture a world where numbers were not written in the form we know today. Thousands of years ago, across vast regions like Mesopotamia and Egypt, humans were just beginning to scratch symbols into bones and clay tablets. One of the earliest glimpses into this is the Unsung bone, found along the border of present-day Uganda and the Democratic Republic of the Congo, dating back to around 18,000 BCE, with marks that could represent early forms of prime numbers, 11, 13, 17, and 19. It's a symbol of how humans started organizing the world around them using numbers. Imagine a group of people gathering around a campfire, tallying up seasons or stars, perhaps not fully understanding their significance, but sensing the power hidden in these symbols. Meanwhile, in Mesopotamia, a more complex numerical system was emerging. The Babylonians created a base 60 system, which is why today we divide circles into 360 degrees and measure time in units of 60 minutes. Picture a scribe sitting in a bustling city, inscribing clay tablets with wedge-shaped cuneiform marks, recording taxes or transactions in a vibrant marketplace. This system didn't have the number 0, but still managed to handle complex algebraic problems, such as calculating land areas and trade quantities. The Babylonians even ventured into geometry, formulating theories that would later be named after Pythagoras. As we move further east, we find ancient China, where mathematics was deeply tied to divination and the natural order. Around 300 BCE, the Chinese used counting rods, bamboo sticks laid out in rows to represent numbers. Imagine a merchant on a dusty trade route, stopping to calculate his inventory with nothing but a handful of rods. While this might seem primitive today, the system was revolutionary at the time, enabling traders to perform multiplication and division, even extracting square roots. Rod numerals also had the conceptual understanding of 0, a placeholder that would take the rest of the world centuries to adopt. One fascinating glimpse into early mathematical thought comes from the 9 chapters on the mathematical art, a collection of Chinese mathematical knowledge from around 1000 BCE. The book was practical, featuring problems like dividing land or calculating taxes. As the author wrote, the mathematics of these chapters will ensure the survival of people through knowledge. This shows us that ancient math was not just an abstract pursuit. It was survival, power, and the key to order in chaotic times. So what's the point of all these stories? These ancient mathematical systems were not isolated innovations. They came from the need to solve real-world problems: how to split land fairly, how to predict celestial events, and how to manage the complexities of early societies. Numbers were not invented by a single civilization, but evolved simultaneously across cultures, proving that human curiosity and the desire to understand the world is universal. The concepts of algebra, geometry, and even our modern numeral system owe their roots to the ancient minds that sought to impose order on a chaotic world. As these early civilizations laid the foundation, the next era would propel mathematics into even greater heights. Trade routes, conquests, and the spread of knowledge set the stage for a mathematical revolution. This brings us to an age of discovery, where curiosity gave way to innovation, and the scattered ideas of the ancients would converge into the groundbreaking work of a few key pioneers. As the 1600s dawned, the world was on the cusp of radical transformation. Across Europe, the old ways of thinking were being challenged, and mathematics was about to play a starring role in this intellectual revolution. The scene is set in bustling cities like Paris and London, where scholars were locked in debates about the nature of the universe, while inventions like the telescope were opening up the heavens for the first time. Enter René Descartes, a French philosopher who forever changed the way we think about geometry. Descartes didn't just see math as a tool for practical purposes. He believed it held the key to unlocking the mysteries of the cosmos. He introduced the idea of coordinate geometry, a system that allowed people to map shapes and objects onto a grid of X and Y axes. Suddenly, what was once abstract could be visualized in a clear, logical way. Imagine Descartes sitting in his study, sketching curves on a piece of parchment, realizing that math could be used not just to calculate, but to describe physical reality itself. Around the same time, across the Channel in England, Isaac Newton was making his own groundbreaking discoveries. By 1666, he had already formulated the basis for calculus, an entirely new branch of mathematics that could measure change. This came from his obsession with motion, gravity, and the forces that controlled the natural world. Picture Newton watching an apple fall from a tree, pondering not just why it falls, but how its speed changes as it moves. His genius lay in realizing that this change could be expressed mathematically. He would later describe this moment as the most profound insight of his life. But Newton wasn't the only one racing to discover calculus. In Germany, Gottfried Wilhelm Leibniz independently developed his own version of calculus around 1675, sparking one of the most heated rivalries in mathematical history. Leibniz's notation, the familiar symbol we still use for integration, was a stroke of genius. Though the Newton-Leibniz controversy over who invented calculus first raged for years, the truth is that both men made extraordinary contributions that would reshape not only mathematics, but physics, engineering, and beyond. This era wasn't just about individuals, though. The Islamic Golden Age, which had thrived centuries earlier, had left a treasure trove of knowledge waiting to be rediscovered by Europeans. Mathematical manuscripts from scholars like Al-Khwarizmi and Omar Khayyam were translated and studied in European universities. Their work on algebra and trigonometry became the bedrock upon which Descartes, Newton, and Leibniz built their theories. As one scholar described, mathematics is a language spoken across time and culture, highlighting how these early Islamic contributions were crucial to the breakthroughs of the 17th century. And so, the story of the Renaissance and Enlightenment is one of rediscovery and innovation. Mathematicians were no longer satisfied with practical problems. They were searching for universal laws that could explain the workings of the entire universe. Their tools, geometry, calculus, and algebra, became the foundation for what we now call modern science. These discoveries weren't isolated to math. They paved the way for advances in astronomy, engineering, and physics that transformed society. As Newton's laws of motion and Leibniz's theories of change found application in the real world, mathematics became essential to understanding everything from the movement of planets to the trajectory of cannonballs. With the groundwork of calculus and geometry laid, the next era would delve deeper into abstract thinking, as mathematicians like Gauss and Euler pushed the boundaries of what numbers could do. The exploration of infinity, complex numbers, and higher dimensions awaited, offering even more profound ways to understand the universe. In the early 19th century, Carl Friedrich Gauss stood at the forefront of a new era in mathematics. Known as the Prince of Mathematicians, Gauss made groundbreaking contributions to number theory, geometry, and algebra. One of his most famous achievements, the development of non-Euclidean geometry, shattered the long-held belief that parallel lines never meet. Imagine a young Gauss, sketching diagrams late into the night, realizing that space might curve, allowing for a geometry beyond the familiar plane. His discovery opened doors to a world where mathematics no longer adhered to simple, observable rules, but instead ventured into abstract ideas that would later become the foundation for Einstein's theory of general relativity. During this period, another towering figure, Leonhard Euler, transformed the landscape of mathematical thought. Although Euler lived in the 18th century, his work on functions, infinite series, and graph theory echoed throughout the 19th century, laying the groundwork for modern analysis. Picture Euler, blind by the end of his life, calculating in his head with such precision that he could derive results faster than others could write them down. His work on complex numbers, numbers that include the square root of -1, was revolutionary, forever changing how we understand equations and functions. Fast forward to the early 20th century, and we find the brilliant yet tragic figure of Srinivasa Ramanujan. Born in 1887 in India, Ramanujan was largely self-taught, working in isolation from the broader mathematical community. When his work eventually reached G.H. Hardy at Cambridge University in 1913, Hardy was stunned by the originality and depth of Ramanujan's ideas, especially in infinite series and partition functions. Ramanujan's intuition for numbers was so profound that Hardy once remarked, "Every positive integer is one of Ramanujan's personal friends." Unfortunately, Ramanujan's life was cut short by illness, but his legacy lives on in formulas still being used in string theory and quantum physics today. At around the same time, Emmy Noether, born in 1882 in Germany, was making her own revolutionary contributions to mathematics. Despite facing discrimination as a woman in the male-dominated academic world, Noether's work in abstract algebra and symmetry was groundbreaking. Her Noether's theorem, which connects symmetry and conservation laws, became essential to modern theoretical physics. Just imagine her in a classroom, passionately lecturing on abstract concepts that even her male colleagues struggled to understand fully. Her determination broke through societal barriers and redefined what was possible for women in mathematics. By the mid-20th century, mathematics had expanded beyond human calculation with the invention of the computer. The theories of Alan Turing in 1936, exploring the concept of an abstract computational machine, opened the floodgates to the modern digital age. Today, these developments underpin everything from cryptography to space exploration. What began as pure mathematical thought, untethered from practical application, now guides rockets to the moon and powers the smartphones in our hands. The legacy of these mathematical giants is that they didn't just solve problems, they invented entirely new ways of thinking. Their abstract theoretical work has found applications in areas they never could have imagined, from quantum mechanics to artificial intelligence. This demonstrates the power of mathematics to leap beyond the page and into the fabric of the universe. As we move forward into the next era, the stage is set for more than just answering questions. We now have the tools to ask questions we never thought possible. This book reveals that much of what we know about mathematics has been filtered through the lens of cultural bias and historical omission. It highlights how civilizations like ancient India, China, and Babylon made revolutionary mathematical contributions that were often overshadowed by European narratives. Stories of forgotten figures, such as Madhava's early work on calculus, showcase the global and collaborative nature of math's evolution. By exploring these hidden stories, the book challenges us to rethink how we credit the advancements that shape our world today. As the editor of Herdley, I believe that through learning from these stories, we can approach the future not just with knowledge, but with the courage to imagine the unimaginable. As we reflect on our journey through this book, it becomes clear that the central argument holds. Mathematical discoveries have often been misattributed, overlooked, or erased, distorting our understanding of history. One particularly striking example is the story of Madhava of Sangamagrama, a brilliant mathematician from India in the 14th century. Long before calculus was credited to Newton and Leibniz, Madhava had already developed many of its core concepts, such as infinite series and the approximation of pi. Yet his contributions remained in the shadows for centuries, known only to a small circle of scholars in the Kerala school. Imagine the world of mathematics if his ideas had been recognized sooner, bridging centuries and influencing the course of scientific development far earlier than they did. This story, like many others in the book, reinforces the idea that our understanding of math has been shaped by powerful forces, often neglecting the global, collaborative nature of its evolution. It invites us to reconsider how we view history and recognize the many unsung trailblazers whose work built the foundations for modern science and technology. As we move toward a future shaped by even more groundbreaking discoveries, it is crucial to remember the importance of honoring all contributors, whether celebrated or forgotten, who have helped expand the boundaries of human knowledge.